Today let's talk about vacuum tubes. And by vacuum tubes I mean electronic vacuum tubes. Electronic because they use electrons inside. There are vacuum tubes that are used for other purposes. For example, some vacuum tubes are used for things like spectral analysis and other things like that, and they're not actually used for electronic purposes. One reason that I digress slightly on that is what I'm going to try to do is to fill in some gaps around the vacuum tube literature that exists, or videology, I guess I should call it, on YouTube. There are a number of videos on how tubes work. In fact, I'll show you one that I did some time ago. The basic idea, though, is I'm hoping that you all either already have that information or you'll go watch those before you complete this one. And instead, I'm going to try to fill in a few gaps. For example, one thing I'm going to be talking about is why all these different styles. Notice this one has a top cap, this one has a little Coke bottle shape. For those of you not old enough to remember when Coke bottles looked like human figures, this bulge that comes out and then comes back again. This one is in all metal, this one has a different kind of base, and so on. So we're going to talk about all of those things. Before we do, let me just give you a quick look at a couple of earlier videos you might want to look at first. Here is a video, my number 81, entitled How Tubes Work. That is a bit more in depth, and it covers the actual operation of tubes. So I suggest, if you would like a little bit of a review, or you maybe haven't looked at how tubes work before, that you take a look at this video. There are many other excellent ones by people like Mr. Carlson, Mr. Carlson's Lab, and so on. I suggest those too. Another one that you might want to look at somewhat the same time is this, my number 82, which is intended as a follow-on to 81, that's called Tube Circuits. And the idea there is, the first video talks about the actual operation of the tube. This video talks about how they are used in circuits, and I recommend that you at least review this level of detail before we go on. You don't need it for the video we're going to make today, but when we get on into radio circuits and troubleshooting and that kind of thing, these would be very helpful if you haven't already know the material. Let's begin by taking a look at a Zenith radio from 1935. This is in Volume 5 of Riders. As I showed you earlier in this series, you can get that at AmericanRadioHistory.com. It is the first page of the Zenith section of Volume 5, Riders, and it shows a TRF, that is a tuned radio frequency receiver, model M601. You'll notice that these, if you don't already know the symbol for a vacuum tube, it generally is a circle like this with some other things drawn on the inside. This tube is the first RF tube, and it's called a Type 35. Then a second RF, Type 35, and then a Type 24 detector, a Type 47 power output tube, and then down here a Type 80 diode rectifier. Now, if some of those terms are unfamiliar to you, we'll talk about them more as we go along. For right now, I'm just giving you this as an overview. So this is a fairly typical set of the early 1930s, and Each stage is individually tuned. One of the problems with these receivers is they tended to go into oscillation. And not only would the squeals upset you and anyone else in the room that was listening, but it also would send out radio signals that would interfere with other receivers in the neighborhood. So particularly in dense areas like New York City, someone turned on their TRF radio, and as they were tuning it, everybody else had to listen to the squeals and howls. So why did the numbers change between these two tubes and this? Well, the reason is the function of this tube is different from the function of these tubes here. These have essentially the same function, which is just to amplify the RF signal. This is the detector. In other words, it is the tube that converts the radio signal into an audio signal. And then the audio signal goes through the power amplifier and goes to the loudspeaker, and this is the symbol out here for the loudspeaker. This is a transformer. It's called an output transformer. After the TRF radios developed so many problems, there was an attempt to move into superheterodynes, which had been invented during World War I. However, the patents for that were owned by RCA. David Sarnoff was a general. He was very aware of the military development of the superheterodyne. And so after the war, he joined what became the Radio Corporation of America. And they basically grabbed up all the patents. Now today you wouldn't be able to do that because, of course, anything developed at government expense can't be monopolized. But back in the day, a general who knew other generals and knew the right people was able to do that. And as a result, RCA monopolized superheterodyne receivers for a very long time. Eventually, by the mid-30s, other manufacturers had found ways either to license or to get around or otherwise to build superheterodyne receivers. So in that same year, Zenith was building a superheterodyne. And this is the schematic of that superheterodyne. It used a tube at the beginning, which in this stage, they call it the first detector. And you remember in the previous example, there was only one detector. In this, there are two detectors, or at least that's what they're called. The first converts the radio signal from its incoming frequency, that is the frequency you tune to a so-called intermediate frequency. And then that intermediate frequency is amplified. So you'll notice that this tube is called an IF. This is called a first detector. And then this is called the second detector. So instead of two RF amplifiers, this has a detector, which also includes an amplifier, and an intermediate frequency amplifier. Then it's detected and goes on to the power output stage into the loudspeaker. But notice that the tube numbering has changed. This is a 6A7, then a 6D6, a type 75 tube, and a type 42 tube. So what does this change from just pure numbers like the 72 and 45 to numbers like 6A7? Well, that was due to an attempt on the part of the radio manufacturers to standardize the tube numbering system. It had really gotten out of hand by the early 30s, and so they adopted a system that used the first digit or the first set of digits, that is all the numbers before the letter, to designate the filament voltage. The lettering designated the particular tube. So an A tube is a tube that does this conversion. It's sometimes called a pentagrid converter tube. It's sometimes also just called a first detector. But at any rate, that's what the A means. And then the 7 referred to the number of elements in the tube. Here is an example of a RETMA numbered tube. Now, RETMA is the more modern name. It used to just be RMA, for Radio Manufacturers Association. Later, when television came in and other electronic came in, they changed the name to Radio Electronic Television Manufacturers Association. So the first digit or digits denotes the filament voltage, as we noted. The S, I'll talk about in a second, talks about it is a single-sided tube. The next letter designates the type. So before they started making single-sided tubes, this would have been called a 6K7. And here is an example of a 6K7. Notice that it has 8 pins on the bottom and a cap on the top. This was a typical 6K7 of the day. This is a 6K7 GT, and we'll talk about that in a second. This is a 6SK7, and we'll also talk about why the S. But a 6K7 would have been this tube with a top cap. In other words, a metal tube. If it used a glass, it would be called a G, and they made them in this style also. So here's the basic idea. Filaments, whether or not it is single-ended, like this tube, where all the elements and everything is connected here, versus this kind of tube that has a top cap, that's what the S stands for. K for the type of tube. The next digits are 7 for the number of elements, and then whether or not it's a glass tube, they add a G. If it is the full-size glass tube like this, then that's all they have. If it is a glass tube in the tubular as opposed to the pinched style, notice that this one, the envelope is pinched up here, then it was called a GT for glass tubular. And then finally, they might add additional letters on the end for revision numbers. By this time, most of the tubes that were being used were 8-pin tubes, and the sockets looked like this. Notice that there are 8 places for pins. By the way, here is an octal socket. This is an empty one. But you notice that there's a keyway here and a key on the bottom. And if you rotate that until the keys line up, right there, then you can plug these together. I won't do that because these are both new. They've never been used. They're what are called new old stock. And so they're a little bit tight. But the idea was 8 pins on the bottom with a keyway to give you so that you can line the pins up. There were other types. For example, a Philco developed an 8-pin variant of the octal tube that they called a loctal. Now this was done for 2 reasons. One was to get around the patents on the octal socket. The second was to provide a locking mechanism. And you may or may not have noticed that one of the tubes that I put down has that locking tab or that locking space here. Let me move this out of the way so the camera will focus a little better. There you see that locking tab locks into this locking ring here. You may notice the ring is open to one side. That is the side where there is a keyway, like the octal, but it gives you a way to open the tube, because what you do is you push away from this little dent on the base. That shows you where the sensitive spot is to open this from its locking position. These were of some benefit in radios like auto radios where they had a lot of vibration. But most of the reason that Philco did this was to get around the octal tube patents so that they could make octal tubes without having to pay patent royalties. Returning to the schematic of the radio that we're using as our example, that is this Watterson Model 4581, notice the tube on the left has 5 grids. The tube in the middle has 3 grids. The tube on the right has only 1 grid. So these were developments in tubes that began with diodes, just 2-element tubes where there's just a filament, maybe with or without a cathode. Sometimes the filament was the cathode, and then a plate. In other words, 2 active elements. But they eventually discovered that you could build a tube with 3 elements, and that allowed you to control the signal. Here, for example, is a schematic that shows a 3-element tube. Notice 1 element is called the grid, 1 is called the anode or plate, and 1 is called the cathode. Now over here you show the construction of a triode tube. This is the heater. It's a little wire that goes up and then comes back down. You put filament voltage through this and it heats the tube up. Then, if you had a separate cathode, that heater would heat that cathode, and electrons would be boiled off and would be available to travel to the plate. If you put a positive voltage on the plate, those electrons will flow to the plate. But if you put a grid in between, then you can control the flow of those electrons by adjusting the voltage on that grid. Once again, if you haven't seen this kind of thing before, I suggest you go watch How Tubes Work, my number 81. Eventually, a type of tube was developed that was called a pentode tube. You notice that this is one that has 3 grids, and this was done. Initially, a grid was put in between to help cut down. Remember I said in the TRF receivers how they would oscillate and howl? Well, by inserting a grid in the middle called a screen grid, they were able to reduce the tendency to oscillate. However, that introduced another problem that we will not get into here, but I talk about a little bit in How Tubes Work, that of secondary emission. In other words, when the electrons hit the plate, they bounce off. And to help that, the designers inserted a 3rd grid called a suppressor grid. Suppressor because it suppressed secondary emission. This is an example of a pentode circuit. Notice, same thing, cathode, you put filament voltage on the filament, or the heater, that heats the cathode. Cathode emits electrons. You put a positive voltage on the plate, and electrons flow, and then you control that flow by putting various voltages on these 3 grids. Once again, on the right is the actual physical construction of these tubes. Notice the plate is a metal structure, usually a solid metal structure with 2 pillars and insulators in between. This is the suppressor grid. This is the screen grid inside of that. Then the control grid inside the screen grid. then the cathode inside the control grid, and finally the heater at the bottom to heat up the cathode. So that's the basic construction of a pentode. Most of the tubes we're going to talk about will either be pentodes or triodes. There was another kind of tube that was developed, once again, largely to get around patent problems, called the beam power tube. And the only difference between this and the pentode is, notice the pentode has a suppressor grid, and the beam power tube just has plates to suppress the emission rather than a grid. And those plates are called beam forming plates, and that is the reason why that a tube like this is called a beam power tube. Now, understand that this tube works almost exactly like the pentode. The major difference is the way the beam power tube suppresses secondary emission. We won't get into that, but here is how it is constructed. Once again, the plate. Then, instead of a grid that is completely circular, there are a pair of plates which basically are just like the plate itself, or the anode, except they're smaller and spaced a little closer together. And that is to focus the electron beam a little harder onto the plate. Then the screen grid, the control grid, the cathode, and finally the heater. So I hope this gives you a bit of an overview on the development of tubes, how they are numbered, and what the various elements are and how they're physically constructed. As I said, I'm not going to talk too much about how they work in circuits. That's, I think, better explained in my number 81 and 82. So if you haven't watched those already, I hope that's piqued your interest. I hope you've also learned something new here. I realize some of you have already heard most of this, but I'm hoping there was at least something new here that you learned. And most of all, I hope you enjoyed watching the video and will stay tuned for some in the future. In the meantime, have a nice day.